Newton believed that gravity existed, sufficient to send us to the moon at any time. We feel trapped in time, questioning if we really understand what it is. Newton's discovery is more than a concept, it's a crucial element that might reveal the mysteries of the universe. The cosmos is presenting itself in a manner more untamed than we anticipated. How does Brian Cox's innovative concept challenge our assumptions about time and its potential implications for the way we see things? As we view Brian Cox's recent incredible notion of time in the enormous universe, we realize there are mysteries surrounding us, awaiting resolution. Many of them have to do with gravity and time, two important components of our reality. People think there might be a planet where time behaves strangely and could accelerate or decelerate. Additionally, the energy that keeps us on the ground may not be what we think it is. Albert Einstein's theories of relativity are useful because they provide a new perspective on gravity and time. This well-known name gave us a novel method to examine the cosmos using his theory of relativity. His research gave us insight into how time behaves in various contexts, such as when things happen very quickly. It all began in the early 20th century when Einstein introduced two major concepts, general and special relativity. In 1905, special relativity altered how we perceive time and space. It simply affirms that the same laws of physics apply to anyone not accelerating, regardless of their direction of travel. This concept raises intriguing possibilities, such as time slowing down or stretching under certain conditions. A compelling explanation of time comes through a thought experiment, the light clock. Picture yourself in a spacecraft traveling very fast, near the speed of light. Inside, a beam of light bounces off two mirrors. According to physics, the speed of light never changes. To an observer outside the vessel, the light seems to follow a longer, angled path. For the outsider, the journey appears longer. Therefore, the light takes more time to complete its journey from that perspective. This time difference is known as time dilation, as defined by Einstein. Time goes more slowly for the individual who is moving than for the one who remains still. Thus, time behaves differently depending on how fast you go. Understanding how things shift as they move reveals relativistic effects. Scientists use massive equipment, like the Large Hadron Collider, to push particles close to the speed of light. When things change so quickly, we must think about time in a unique way to get accurate measurements and forecasts. Special relativity, shared by Einstein in 1905, changed our view of the cosmos, especially concerning motion and time. This notion suggests that physics rules are the same for everyone, even if this differs from everyday experience. According to Einstein, the speed of light is the highest possible speed. Because of this, events that seem simultaneous to us may not appear that way to someone traveling near light speed. Another concept derived from this is length contraction. Objects appear shorter when observed from a stationary position while they move at high speeds. The famous equation E=mc² demonstrates how mass and energy can transform into one another. This is essential to understanding how small particles behave while traveling quickly and helps explain phenomena like nuclear reactions. Relativity is more than an idea, it's useful in real-world situations. For example, we rely on it in technologies like GPS. When GPS satellites provide your device with signals, time dilation must be accounted for. Otherwise, your location data would be completely inaccurate. Thus, we learn from special relativity that time is not constant. It depends on how things are changing, which interferes with the way we perceive time and space. Our typical perspective of the cosmos is flawed. Time, as altered by motion, redefines fundamental ideas, such as the constant speed of light and how energy and mass are connected. But relativity goes further. In 1915, general relativity explored how gravity connects with the structure of the universe. It modified the old idea of gravity as just a pulling force. Instead, it stated that gravity arises from the curvature of spacetime. It's not an invisible force but simply the path objects follow due to the bending of space and time. Brian Cox explains general relativity by considering spacetime as a large, flexible sheet. When something massive, like a planet or a star, sits on it, the sheet dips. Smaller objects nearby roll toward it, not due to an invisible force, but because of the curvature. General relativity describes planetary motion accurately, including the way they orbit the sun, more effectively than older models. The idea is that time and space are twisted, like a pliable fabric, which explains cosmic behavior better than Newtonian gravity. One of the earliest confirmations of general relativity came in 1919. During a solar eclipse, Sir Arthur Eddington's team observed how starlight bent around the sun, just as Einstein had predicted. This validated the theory. Gravity also affects the passage of time. Where gravity is strong, time moves more slowly than where it is weak. For example, near a black hole, your clock would run more slowly than one farther away. Black holes are extreme areas where gravity is so strong that even light cannot escape. The event horizon is the point of no return. Once crossed, nothing escapes. Einstein's theory predicted such phenomena, and later observations confirmed their existence. General relativity added structure to our understanding of the cosmos. Einstein initially included a cosmological constant in his equations, assuming the universe was static. Later, it was discovered the universe is expanding, an idea foundational to the Big Bang theory. Another major prediction of general relativity was gravitational waves, ripples in spacetime caused by massive objects moving quickly. In 2015, LIGO scientists detected these waves, proving Einstein's predictions once again. Some question whether gravity is a fiction, not in the sense of non-existence, but that our understanding might still evolve. Science often challenges conventional beliefs. Some propose modified theories like MOND, modified Newtonian dynamics, which suggest gravity acts differently at low speeds, particularly in dark matter-dominated galaxies. Others believe dark matter and dark energy, used to explain space-related phenomena, might be unnecessary if gravity is better understood. New ideas, like unknown particles or forces, are being explored as alternative explanations. Science thrives on testing these fresh theories rather than discarding them prematurely. Einstein's ideas have also influenced time travel discussions. Theoretical constructs like wormholes and chronology protection, Stephen Hawking's idea, aim to explore whether backward time travel could be possible, though it remains unlikely. Gravity may one day be explained by ideas that align better with known facts, but Einstein's general relativity remains the most successful and predictive model we have. It explains phenomena like light bending, planetary orbits, and time dilation with great accuracy. Let's explore how this affects space travel. Life on Earth mostly occurs in space, and space travel is both exciting and challenging due to its vastness. Even with advanced technology, switching between stars is difficult. Consider the twin paradox. One twin stays on Earth, while the other. Understand the one-way flow of time, what we often call the arrow of time. We must accept that entropy is not just a background concept, but a fundamental force that gives time its direction. As entropy increases, systems naturally evolve from a state of order to a state of disorder. That's why we remember the past but not the future. The past was more ordered, while the future holds more possible, chaotic configurations. This thermodynamic principle doesn't just apply to broken eggs or melting ice, it shapes the very way we experience the passage of moments. Brian Cox and others suggest that if time's arrow is tied to entropy, then the universe's beginning must have been a remarkably low-entropy event. The Big Bang, in this view, wasn't just the start of space and time, but the start of order itself. The expansion of the universe isn't just spatial, it's temporal, driven by the increase of entropy. And as galaxies form, black holes grow, and stars collapse, the overall disorder of the cosmos continues to rise. This increasing entropy is why we age, why we can't unburn wood, and why time machines remain fiction. Even if we could bend spacetime through wormholes or near light-speed travel, we would still confront the laws of thermodynamics. Entropy would prevent us from looping time backward in any meaningful way. That's part of Stephen Hawking's chronology protection conjecture, which implies nature conspires to prevent paradoxes. Einstein's relativity and entropy together offer a profound, if humbling, vision of reality. Time isn't a universal rhythm ticking everywhere the same. It's flexible, tangled with motion, gravity, and disorder. GPS systems, satellite clocks, and particle accelerators prove these ideas daily, not just in theory but in practical application. Without accounting for relativistic time dilation and entropy-related phenomena, many of our technologies wouldn't function accurately. So when Brian Cox challenges our traditional understanding of time, he's inviting us to grasp a larger truth, that time is not absolute, not even linear in the cosmic sense. It's dynamic, shaped by the structure of the universe and the entropy within it. His vision urges us to look beyond simple hours and days, and instead view time as a cosmic process, intricately linked to gravity, motion, and the inevitable march toward disorder. Demonstrate this. Think about the comparison of a castle made out of sand. It symbolizes a low-entropy condition, characterized by a high level of order. Over time, because of natural phenomena like erosion and wind, the sandcastle will eventually turn into a beach pile, a higher entropy state. This transformation is a prime example of systems' inherent propensity to change in the direction of more chaos, demonstrating that time moves in a single direction. From box learning, gravity, and the future, and the structure of spacetime, which is built upon the creation of the general relativity hypothesis by Einstein, gravity is more than just a force. It's an expression of the curved shape of spacetime, brought on by energy and mass. Large objects such as planets and stars distort the spacetime fabric, and this curvature determines how an item moves, including light. This groundbreaking shift in our comprehension changed our perspective, from considering gravity to be a force, to recognizing it as the outcome of spacetime geometry. A powerful illustration of this idea is the measurement of gravitational lensing, where light from far-off stars bends around large objects such as galaxies. This bending is caused by the galaxy's mass, which bends the spacetime the light passes through, changing its course. These occurrences provide concrete proof of the dynamic interaction between the organization of mass energy and black hole singularities in spacetime. Spacetime is one of the most fascinating aspects of general relativity's predictions. It includes areas of spacetime where black holes exist, where gravity is so strong that not even light may escape. The singularity of a black hole is a point where spacetime's curvature becomes infinite, where our current knowledge and the laws of physics break down. The event horizon denotes the line that nothing may cross, rendering black holes both mysterious and fascinating topics of research. Current developments in technology, like the Event Horizon Telescope, have made it possible for scientists to take pictures of entire black hole event horizons. These supply actual data that supports theoretical models. However, these findings not only confirm features of general relativity, but also provide fresh opportunities to investigate the basic nature of space, time, theoretical gravity, and even time travel, its possibilities and limitations. The idea of time travel has long been a topic of interest and conjecture. In the context of general relativity, some answers, according to Einstein's field equations, suggest the potential for closed time-like curves in spacetime that may circle back on themselves, making it theoretically possible to go back in time. But these solutions often entail unusual circumstances, such as the existence of imaginary or negative energy or wormhole-like structures. Physicist Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics may prevent time travel to avoid paradoxes and inconsistencies. Time dilation, a relativistic phenomenon where time passes at different speeds for observers in relative motion, has been demonstrated by experiments and has applications that echo science fiction. However, such forms of time travel remain purely hypothetical and unverified. Current events and mathematics in the cosmos. Mathematics acts as a medium through which the laws of nature are expressed. Physicist Brian Cox highlights that our experiences teach us that natural rules truly exist. Patterns in the behavior of objects suggest that the best way to communicate these rules is through mathematical language. This viewpoint underscores the profound relationship between mathematics and the physical world, demonstrating our ability to predict and describe natural phenomena using mathematical models. The development of mathematical models, like tensor calculus in general relativity, has played a critical role in making precise predictions that explain gravitational behavior and spacetime curvature. These mathematical tools allow physicists to make accurate forecasts and gain deeper insight into the mechanisms of the universe's expansion and structure. Cosmic expansion and the Big Bang. Studies of distant galaxies reveal that the universe is expanding, with galaxies moving away from us at speeds proportional to their distances. This occurrence, captured in Hubble's law, supports the idea of a single origin point for the universe, commonly referred to as the Big Bang. The discovery of the cosmic microwave background radiation offers further evidence of the universe's hot, dense beginnings, giving us a glimpse into the early cosmos and supporting the Big Bang model. Recognizing the expansion of the universe not only informs us about its origins, but also about the ongoing development and ultimate fate of the cosmos. In summary, the interdependence of time, gravity, and the universe reveals a cosmos far more intricate and interconnected than our everyday observations suggest. From the curvature of spacetime that governs planetary movements to the enigmatic properties of black holes, these concepts challenge our understanding and invite deeper exploration. As scientific knowledge evolves, the interaction between time, gravity, and the universe continues to fascinate and expand our grasp of the cosmos' fundamental workings. Even in simple observations, like stirring liquid or melting ice, we perceive time's one-way flow, shaped by entropy and the universe's underlying structure. This investigation into gravity and time reveals not only the dynamic nature of our universe but also the deeply interconnected fabric that shapes every aspect of reality. Time, gravity, and the expansion of space all play pivotal roles in the ongoing dance of creation and transformation that characterizes the cosmos. The more we understand the delicate interplay of mass, energy, and spacetime, the more we can explore new frontiers, whether it's the possibility of time travel, the elusive nature of black holes, or the expansive universe itself. While our grasp on these phenomena is still in its infancy, the progress made in understanding the nature of gravity, the curvature of space-time, and the behavior of light offers a profound perspective on the universe's origins and its eventual fate. The fact that science continues to uncover these mysteries, whether through mathematical models, technological innovations like the Event Horizon Telescope, or the study of far-off galaxies, reminds us of the vastness of our knowledge still to be gained. But it also reinforces the idea that time, space, and gravity are not isolated concepts but integral parts of a much greater, cosmic story. By continually pushing the boundaries of our understanding, we might one day fully comprehend the true nature of time itself, how it shapes the universe, and how it may, perhaps, allow for the exploration of distant moments or eras. In the end, our journey into understanding the cosmos is not just about discovering the forces that govern it, but about unraveling the profound interconnectedness that exists between all things, human, cosmic, and beyond.